Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great and having a good time. So people, before starting the session, just let me know in the chats if I'm audible and visible to everyone. Hello Fazan, hello Sirat, hi Ashwarya, hi Sharanya, hi Nitish, hello Ahana, hi Sahil, hello Vivek, hello Ubad. Welcome back everyone. Hello Nazima, hi Chitra, hi Sabarish, hello Varsha, hi Ishpreet, hello Madhu, hi Raghavi, hello Danish. Just let me know people in the chats if I'm audible and visible to everyone. Give me some green signal from the chat box if I'm audible and visible to everyone so that we can start the session directly. Yeah. Yes. Perfect. All right, I'm doing great, Ishpreet. How are you? I'm doing good. It's okay, Ashwarya. You can attend the session. Hello, Ashay. Welcome. You're my long-term student, yeah? Welcome to the YouTube session. Perfect. So, people, as you all must be knowing, in the last session of chemical bonding, we discussed about the valence bond theory, right? We exactly saw how covalent bonds are formed, right? And if you remember, I told you covalent bonds are formed by the overlapping of atomic orbitals of two bonding atoms, right? And how did we define overlapping of atomic orbitals? Overlapping used to be defined as the penetration of atomic orbitals of different atoms, of different bonding atoms into each other, right? And that overlapping used to be of two types. One we used to call as axial or head-on overlapping, right? Which always led to the formation of the sigma bond, yeah? And one more was the parallel overlapping, lateral overlapping, sideways overlapping, right? And that parallel overlapping leads to the formation of the pi bond, right? And at the end, if you remember, we saw the structures of different molecules, yeah? We saw the strength of sigma and pi bond, right? And as you remember, I told you, sigma bonds are comparatively stronger than that of pi bonds, and there were two reasons for that. One was your energy factor, yes, right? Energy factor used to show us how exactly sigma bonds are stronger than that of the pi bonds, right? Those are the things which we discussed in the last session. I hope you remember all of them, right? So what all things we are going to cover in the tonight's session? In the tonight's session, we'll be discussing about something called as hybridization. Again, one of the most important topics from the chapter chemical bonding. Yeah. So before starting the session, the ones who have just joined in, who are new to the channel, let me introduce myself. Well, people, my name is Wassim Sir, and I'm your chemistry master teacher right here on this NEET Elite channel. Yeah. The ones who have not liked the video yet, please do like the video, share the video with friends. Do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I take live on this NEET Elite channel. Yeah. So do like the video, share the video with friends, and do subscribe to the channel as well. Okay. All right. So you guys can let me know in the chats if you all are super duper excited for the tonight's session as well. Yeah. You guys can let me know in the chats if you all are super duper excited about the tonight's session. Yes, I'm doing good, Sanjay. How are you? Perfect, guys. Just give me a second. We'll be starting, yeah? Just give me a second. All right, so let's get going. Let's get started with something called as hybridization, okay? So first of all, let me tell you exactly what was the need of this concept hybridization, why this concept of hybridization was given, right? So I'm marking the heading over here as need for hybridization. Why this concept of hybridization was introduced, right? Let's talk about that first. And once you get to know why this concept of hybridization was introduced, then we'll be talking about the actual concept of hybridization, yeah? Okay? Have a look exactly what I'm going to talk about. For example, I'm taking a molecule CH4, right? You all must be familiar with this molecule, CH4, methane we call it, right? This is methane. First of all, in this methane, the central atom is carbon, right? The central atom is absolutely carbon in case of your methane. Okay, the central atom is carbon. If I want you guys to write the outermost electronic configuration of carbon, I'm sure you can do that. It's going to be 2s2, 2p2. This is the outermost configuration of carbon when carbon is present in its ground state. Right? When carbon is present in its ground state, its outermost configuration is going to be 2s2, 2p2. Yeah? The configuration is going to be like this: 2s containing 2 electrons, right? And in case of 2p, there are 2 more electrons, right? 1 electron over here, 1 electron over here, correct? So if you look at this CH4, in case of CH4, how many bonds do we have? We have got 4 sigma bonds basically in CH4. There are 4 bonds which this carbon is making in CH4, right? In CH4, there are 4 sigma bonds being made, right? And in this ground state electronic configuration, how many orbitals are there which have got unpaired electrons? In the ground state electronic configuration of carbon, there are only 2 atomic orbitals containing the unpaired electrons, right? Yes, there are only 2 atomic orbitals which contains the unpaired electrons. But carbon is making 4 bonds. So in order to make 4 bonds, this carbon should have 4 orbitals carrying the unpaired electrons, right? Yes. See, as per the ground state electronic configuration, this carbon has got only 2 orbitals with unpaired electrons, right? But this carbon, it has to make 4 bonds, right? So over here, there should be some 4 atomic orbitals containing the unpaired electrons. So what is going to happen? I'll say excitation is going to take place. Excitation is going to take place. One of the electron from 2s will enter into 2p, right? So the configuration now becomes like this: 1 electron in 2s and 3 electrons in 2p, right? This is something which I call as the excited state of this carbon. This is something which I call as the excited state of the carbon, right? Now guys, have a look. So how many orbitals are there in the excited state of carbon containing the unpaired electrons? There are 4 atomic orbitals in carbon containing the unpaired electrons, right? This is the 2s atomic orbital carrying 1 electron. This is, for example, 2p atomic orbital carrying 1 electron. This is 1 more 2p, and this is 1 more 2p atomic orbital carrying 1 electron, right? Okay. Now, people, what is going to happen over here? What is going to happen over here? This is 2s. It is spherical in shape, right? This is 2p, which is dumbbell in shape. 1 more 2p, dumbbell in shape. 1 more 2p, dumbbell in shape, correct? Now, we know this carbon is forming 4 sigma bonds with 4 different hydrogen atoms, right? Carbon is forming 4 sigma bonds. And sigma bonds are formed by the axial overlapping, right? By the direct head-on overlapping, correct? So, I'll say this is the outermost configuration of the excited state of the carbon, right? It contains 4 atomic orbitals with the unpaired electrons. Now, I'll say one of the hydrogen will come from this side and will start overlapping with this 2s atomic orbital of carbon. One more hydrogen will come from this side and will start the overlapping with this 2p atomic orbital of carbon. One more hydrogen will come from this side, one more hydrogen will come from this side, and they will start doing the overlapping, right? Yes. Now, in case of hydrogen, what is the configuration? 1s1 configuration, right? The configuration of hydrogen is 1s1. So basically, it is the 1s orbital of hydrogen which is coming from here for the overlapping, right? Similarly, it is the 1s atomic orbital of all the hydrogen atoms, right, which are coming for the overlapping. This is 1s atomic orbital of hydrogen, 1s atomic orbital of 1 more hydrogen, 1s atomic orbital of 1 more hydrogen, and 1s atomic orbital of 1 more hydrogen, right? So what has to happen? 4 sigma bonds have to get formed, right? In order to form 4 sigma bonds, there should be head-on overlapping. There should be axial overlapping, right? So there will be axial overlapping between this 2s atomic orbital of carbon and 1s atomic orbital of hydrogen, right? There will be axial overlapping. Over here, there will be axial overlapping between 1s of hydrogen and 2p of this carbon. Again, axial overlapping, right? So 4 sigma bonds will get formed. 4 sigma bonds will get formed. Due to the axial overlapping of 1s atomic orbital of hydrogen and 2s atomic orbital of carbon, there will be 1 sigma bond getting formed. Now, one more axial overlapping between this 1s atomic orbital of hydrogen and 2p atomic orbital of carbon. Again, sigma bond will get formed. Again, sigma bond. Again, sigma bond. So, how many sigma bonds got formed? 4 sigma bonds got formed, right? Are these 4 sigma bonds of same type? I'll say the 4 sigma bonds are not of same type. This sigma bond, this first sigma bond, it got formed between the overlapping of 2s atomic orbital of carbon and 1s atomic orbital of hydrogen. This sigma bond which got formed, it is formed between 1s atomic orbital of hydrogen and 2p atomic orbital of what? Carbon. Similarly, this is also 1s and 2p atomic orbital of carbon. 1s atomic orbital of hydrogen and 2p atomic orbital of carbon, right? Yes. And in the last session, if you remember, I told you in the last session, strength of the bond is directly proportional to extent of overlapping, right? Strength of bond formed is directly proportional to extent of overlapping. More the extent of overlapping, stronger is going to be the bond. See, if I ask you, is the extent of overlapping same in all these four cases? I'll say extent of overlapping is not same in all the four cases. Over here, this is SS overlap. This is SP overlap. Again SP, again SP. Basically, these three overlappings, these three overlaps, they are of same type, but this one is different. Right? So strength of these three bonds is going to be same, right? Which is going to be different than that of the strength of this bond, this sigma bond, which got formed between 2s and 2s, right? Yes. So people, I'll say the sigma bonds which are being formed, right, due to the overlapping, I'll say extent of overlapping is actually different. If extent of overlapping is different, strength of bonds is different. And if strength of bonds is different, I'll say the bond lengths between carbon and hydrogen, they are going to be different, right? So whatever is going to be the bond length between this carbon and this hydrogen, right, that is going to be different than that of bond length of CH bond between this carbon and this hydrogen, right? So if we talk about CH4 molecule, as per VBT is concerned, all the bond lengths must not be equal, right? Because out of the four bonds, one of the bond is formed by, for example, SS overlap. Let's assume this is formed by SP overlap, this also formed by SP overlap, this also formed by SP overlap, right? So no doubt, these three bond lengths should be same, but this bond length should be different. But experimentally it has been observed, practically it has been seen. In case of your CH4, all the four bond lengths are equal, right? In order to explain why in case of CH4, all the four bond lengths are equal, yes, we need the concept of hybridization. I hope you got to know why this concept was introduced. The concept was simply introduced in order to explain the same bond lengths in case of CH4, whereas if CH4 is formed as per VBT, all the bond lengths should not be same, right? But experimentally it was seen that all the bond lengths are same in case of CH4. So in order to explain all the same bond lengths in CH4, a concept of hybridization was introduced. You can let me know in the chats if it is clear till here, then only I can start something called as hybridization. Let me know in the chats, guys. Let me know in the chats fast. Let me know in the chats fast. Yeah? Is everything clear till here? Is everything clear till here? Let me know fast in the chats, guys. Fast. Yeah? Sir, in NO3, hybridization is 3. What does that mean? It is making 3 bonds. Does it mean that it has 0 lone pairs? Munish, just wait for it. You'll get the concept of hybridization in some time. Just wait for it, okay? This question will get cleared in some time. You just let me know, is everything clear till here, what have I taught till now? Yeah? Okay, so if it is clear, then let's move on to the actual concept of hybridization, right? Let's move on to the actual concept of hybridization. Now let's exactly see how come hybridization is going to explain the same bond lengths in case of CH4. Have a look, guys. The first point which I want you guys to understand about hybridization, it is a complete hypothetical concept. It is a complete hypothetical concept. It does not have any experimental background, right? This hybridization, it's a hypothetical concept. It does not have any experimental background. Point number 1. Point number 2, what this hybridization means. Hybridization is defined as, the mixing of atomic orbitals. The mixing of atomic orbitals belonging to the same atom, but having slightly different energies, so that a redistribution of energy takes place, which leads to the formation of new orbitals which are identical in all the respects, and those new orbitals were termed as hybrid orbitals. What that means, you'll be getting this concept in some time, right? First, I want you guys to remember this. Hybridization, it is basically defined as the intermixing of atomic orbitals, of a particular atom, right? The intermixing of atomic orbitals of particular atom, right? Which have got slightly different energies. Yes, so that redistribution of energies takes place, which leads into the formation of new orbitals which are identical in all the respects, be it shape, be it energy, everything. And those new orbitals which got formed by the intermixing of atomic orbitals of a particular atom, right? Those new orbitals formed were called as hybrid orbitals, right? Yes. What that means, you'll get the idea in some time, right? See guys, in the atom, there are basically atomic orbitals. Now, during the bond formation, first, the atomic orbitals of the atom, they are going to intermix. And when they will intermix, they will lead to the formation of hybrid orbitals, right? And this is the shape of the hybrid orbital, okay? One of the lobe will be bigger in size and one of the lobe will be smaller in size. Yes? One of the lobe will be bigger in size, one of the lobe will be smaller in size. Yeah? Okay? Let me tell you one more thing. In case of hybridization, the bond formed is strong because more is the extent of overlapping. See, first of all, whenever there will be bond formation between two atoms, whenever there is a bond, there is going to be the bond formation between two atoms, right? First, the atoms will undergo hybridization. In the atoms, the orbitals will start intermixing. They will lead to the formation of hybrid orbitals. And once the hybrid orbitals are formed, the hybrid orbitals once formed, they are going to overlap with the orbitals of the other atoms, right? They are going to start the overlapping afterwards. And due to the overlapping, definitely we know bonds are formed, sigma bonds are formed, yes, right? So do remember this concept. In case of hybridization, the bond formed is strong because of more extent of overlapping. So first of all, in the atom, hybridization is going to happen, intermixing of atomic orbitals is going to happen, which will lead to the formation of hybrid orbitals. And once hybrid orbitals are formed, then hybrid orbitals are going to do the overlapping and they will lead to the formation of covalent bonds. They will lead to the formation of sigma bonds, right? And pi bond also in one case. That's something which I'll be showing you in some time, right? Yes, since the size of the lobe, size of this lobe, size of the hybrid orbital is bigger. So when this hybrid orbital undergoes overlapping, when it overlaps with the another orbital, right? Yes, extent of overlapping will be more. And more the extent of overlapping means more is going to be the strength of the bond. As simple as that. Yes? Right? These are few points which you need to take a note of first of all. Then I'll teach you the hybridization in detail, right? Okay. Remember, the number of atomic orbitals which are going to intermix for hybridization, right? The number of atomic orbitals which are going to intermix is always equal to the number of hybrid orbitals formed. If in the atom, 2 atomic orbitals will intermix, that means 2 hybrid orbitals will get formed. If 3 atomic orbitals will intermix, 3 hybrid orbitals will get formed. So remember, the number of hybrid orbitals formed is always equal to the number of atomic orbitals intermixed. Yeah? Do remember this thing as well. And in case of hybridization, half-filled, fully filled as well as empty orbitals. Half-filled, fully filled as well as empty orbitals. They can participate in the intermixing. They all can participate in the hybridization. Example I'm going to give you in some time, yeah? Right? Overlapping of hybrid orbitals leads to the formation of sigma bonds except in benzene, right? See, once the hybrid orbitals in the atom are formed, these hybrid orbitals are going to show the overlapping, right? Yes? And the overlapping of these hybrid orbitals, they are always going to lead to the formation of the sigma bonds, except in case of benzene, where the overlapping of your hybrid orbitals will lead to the formation of the pi bond, right? This is something which I'll be teaching you in detail, right? Hybridization takes place at the time of the bond formation. It does not take place in the isolated atom. Whenever I'll be having the isolated atom, which is not going to form any bond with any other atom, right? Hybridization does not take place in the isolated atom. It takes place at the time of the bond formation. Whenever the atom has to make a bond with some another atom, at that time only hybridization is going to take place. Otherwise, hybridization is not going to take place. Yes, in the isolated atom, hybridization is not going to take place. Correct? I'm sure you would have taken the note of all these points, right? And people, understand, once the hybrid orbitals are formed, yes, they will start doing the overlapping, right? And overlapping of hybrid orbitals will lead to the formation of sigma bonds, right? The hybrid orbitals containing the electrons are going to orient themselves in such a way that there are minimum repulsions between them and maximum stability. What that means, this is something also which I'm going to explain sometime, right? First of all, these are few points related to the hybridization. Now let's understand the actual concept of hybridization. Let's understand all these points in detail now, right? One by one. These were all the points. I'm sure you would have taken the note of all these points, right? See guys, before talking about the concept of hybridization, right? Let me tell you one important thing. See guys, understand. There is a method by means of which we calculate hybridization, yes, of the central atom, right? That method is called as steric number method. That number is called as steric number method. Steric number method is the one by means of which I can check the hybridization of any atom in the molecule, right? Have a look. Remember, steric number is nothing. It is the number of sigma bonds plus number of lone pairs. I'll show you exactly how to calculate sigma bonds as well as lone pairs, right? Yes. Remember, if steric number value comes out to be 2, the hybridization involved in the molecule is going to be sp. And if the hybridization involved in the molecule is going to be sp, the geometry of the molecule is going to be linear. Point number 1. If the steric number is 3, hybridization involved is going to be sp2. I'm going to teach this in detail, right? First of all, I'm giving the quick overview of things. Yeah? Quick overview of things. If the steric number is 3, the hybridization is sp2 and the geometry of the molecule is going to be trigonal planar. It's going to be trigonal planar. Yes. Similarly, if the steric number value comes out to be 4, the hybridization is going to be sp3, and in case of sp3 hybridization, the geometry is going to be tetrahedral. Yes. Similarly, if the steric number value comes out to be 5, the hybridization is going to be sp3d, right? And it's going to be trigonal bipyramidal. The geometry of the molecule is going to be trigonal bipyramidal. Right? Similarly, if the steric number value comes out to be 6, hybridization involved is going to be sp3d2 and the geometry is going to be octahedral. Yes? And if the steric number comes out to be 7, the hybridization is going to be sp3d3. Yes? And the geometry is going to be pentagonal bipyramidal. This is something, this table I want you guys to remember first of all, and now I'm going to teach you this hybridization in detail, right? Right, people? Perfect. So let's try to understand this hybridization through the actual molecules now. Okay, now you're going to understand the concept of hybridization. Okay, till now it was all theoretical, right? I just wanted you guys to note down every point. Okay, and I'm sure you have noted down every point. Now let's start the concept of hybridization exactly. See, first of all, I'm starting with the molecule BeF2. Let's say I'm taking the molecule BeF2, correct? This is the molecule BeF2. Understand? This B is the central atom first of all, right? It's a central atom. This beryllium, it belongs to group second elements. And group second elements, they have got 2 electrons in their valence shell. So how many valence electrons are there with beryllium? There are 2 valence electrons with the beryllium, right? So 2 valence electrons. First, I calculated the valence electrons of the central atom, right? This beryllium, how many sigma bonds it is forming? This beryllium, how many sigma bonds it is forming? Since beryllium is the central atom and fluorine, these are the terminal atoms. Remember, the number of terminal atoms is always equal to the number of sigma bonds. So beryllium is forming 2 sigma bonds. The number of terminal atoms is always equal to the number of sigma bonds, right? Now, after getting to those sigma bonds, let's calculate the lone pairs. Let's calculate the lone pairs. See, this beryllium, it had 2 valence electrons. It had 2 valence electrons. And it's forming 2 sigma bonds at the same time. So this beryllium is using all its 2 electrons to form 2 sigma bonds. So there will be no lone pair as such on beryllium. So sigma bonds 2, lone pair 0. Let's calculate the steric number, right? Let's calculate the steric number. Steric number is nothing. It's going to be sigma plus lone pair. Sigma bonds are 2, lone pair is 0. So the steric number value comes out to be 2. And if the steric number comes out to be 2, hybridization involved is going to be sp. Hybridization involved is going to be sp, absolutely, right? You got to know the hybridization involved, that is going to be sp, yeah? Yes. Since the hybridization involved is sp, so you can talk about the geometry of the molecule as well. It's going to be linear, right? Now let's try to understand this BeF2 in detail. So this is something which we got to know about BeF2, right? Now guys, have a look. If I talk about Be, what is the outermost configuration of Be. Hydrogen, helium, lithium, beryllium, right? Its actual configuration is going to be 1s2, 2s2. There will be 2p also, but this 2p does not contain any electron, right? So we will have a look exactly. 2s is containing 2 electrons and 2p is containing 0 electrons, correct? 2p is containing 0 electrons, right? In case of BeF2, this beryllium, it's forming 2 sigma bonds. It's forming 2 sigma bonds. Do we have any unpaired orbital right here? We have no unpaired orbital, right? So what I'll be doing first of all, let's say excitation took place, one of the electron entered into this, right? Yes. So what is going to be the excited configuration of this beryllium? The excited configuration of beryllium is going to be like this. 2s containing 1 electron and 2p containing 1 electron. This is the ground state electronic configuration. This is the excited state configuration, right? I'm talking about beryllium, okay? Now guys understand. Have a look exactly. See, since the hybridization involved in BF2 is sp, that means this s orbital and this p orbital, they are going to intermix. This s and this p, they are going to intermix. So 2 atomic orbitals are going to intermix. One is s and one is p. And the number of atomic orbitals which will be intermixing will be always equal to the number of hybrid orbitals formed. If 2 atomic orbitals are intermixing, so 2 hybrid orbitals will be getting formed, right? And how do we represent the hybrid orbitals? This is the shape of hybrid orbitals. So 2 hybrid orbitals are being generated by the intermixing of these 2 atomic orbitals. So which hybridization is involved? sp hybridization is involved, right? I'll be calling this hybrid orbitals as sp hybrid orbital. Even this I'll be calling as the sp hybrid orbital, right? Now these two sp hybrid orbitals, right? They'll be identical in all the respects, right? They'll be identical in all the respects. Their shape is same, their energy is same, everything about them is same, correct? Once hybrid orbitals are formed, 1 electron over here, 1 electron over here. So this hybrid orbital will contain 1 electron, this hybrid orbital will contain 1 electron. Now these hybrid orbitals containing electrons, they are going to arrange themselves in such a way that there should be minimum repulsions between them. So how they are going to arrange themselves? See guys, see how these hybrid orbitals are going to arrange themselves. This is one hybrid orbital containing 1 electron. This is one more hybrid orbital containing 1 more electron. So these hybrid orbitals, they have arranged themselves in such a way that there is minimum repulsion between them, correct? Right? Now, what is going to happen after this? See, this is beryllium, correct? Now, one of the fluorine will come from this side and one of the fluorine will come from this side, and we'll start doing overlapping with these hybrid orbitals, right? And how they are going to do the overlapping, have a look. If I talk about the configuration of fluorine, the fluorine's outermost configuration is 2p5, right? Fluorine's outermost configuration is 2p5. 1, 2, 3, 4, 5. Let's assume this is px, this is py, this is pz. So px atomic orbital of fluorine is unpaired, right? So px atomic orbital of fluorine will come from this side and will do the overlapping, right? Will do the overlapping. Yes. Similarly, for one more fluorine atom, one more px of one more fluorine atom will come from this side and will do the overlapping. Yes. Is it the axial overlapping? Absolutely, it's the axial overlapping. Axial overlapping always leads to the formation of sigma bonds. So this is one sigma bond which got formed over here. This is one more sigma bond which got formed over here. Well, people, this sigma bond is formed by the overlapping of sp hybrid orbital of beryllium and pure p orbital of what? Fluorine, right? So this sigma bond, it's formed by the overlapping of sp hybrid orbital of beryllium with what? With pure p orbital of fluorine. Even this sigma bond, it got formed by the overlapping of sp hybrid orbital of beryllium with the pure px orbital of one more fluorine, right? So I'll say overlapping in both the scenario is same, right? Overlapping same in both the cases, right? Overlapping is same type of overlapping, right? So same will be the extent of overlapping. If same is the extent of overlapping, same is going to be the strength of these two bonds, right? If same is the strength of these two bonds, same is going to be the bond length, right? So finally, we represent it like this. This is beryllium at the center. On this side, there'll be one fluorine. On this side, there is one more fluorine, right? What is the angle between the two? Angle between these two bonds, that means I'm talking about the bond angle, it is 180 degree. What was the hybridization involved? Hybridization involved was sp. What is the shape? Shape is simply linear, right? I hope you got the exact concept of hybridization and you saw exactly how this BeF2 gets formed. I'm sure it's clear to everyone. You can let me know in the chats. You can let me know in the chats, guys. Yeah? Right? BeCl2 is going to show the similar structure. Okay? Let me give you one more example. Aman, BeCl2 is going to follow the same thing, right? Exact similar process will be from before BeCl2. BF2 and BeCl2, they are of same type. They're of same type. Let me give you one more example. With that, hybridization will be properly clear to you, right? Let me take the second molecule, which is, for example, BF3. Understand now. This is BF3. This is BF3. First of all, let me use the steric number method and calculate the hybridization of this BF3, right? Yes. Let me use the steric number method and calculate the hybridization of this BF3. So first of all, let me identify the central atom. This boron is the central atom. Boron is the central atom. Boron is a group 13 elements. Sorry, boron is a group 13 element. And how many valence electrons are there with boron? There are some 3 valence electrons with boron, right? How many terminal atoms are being attached with boron? There are 3 terminal atoms attached with boron. Yes. Number of terminal atoms is always equal to the number of sigma bonds. So boron is forming 3 sigma bonds. Boron had some 3 valence electrons, and it's using all these 3 valence electrons to form 3 sigma bonds. So will there be any lone pair as such on boron? There'll be no lone pair as such on boron, right? Yes. If there is no lone pair, if I ask you what about the steric number? Steric number is basically sigma plus lone pair. 3 plus 0 comes out to be 3. And when the steric number is 3, hybridization involved is going to be sp2. And when the hybridization is sp2, the geometry is going to be trigonal planar. Trigonal planar. And remember, the bond angle is going to be 120 degree, right? Now let's try to understand how this molecule actually gets formed. Let's try to understand how this molecule actually gets formed. Have a look exactly. If you talk about boron, right? Hydrogen, helium, lithium, beryllium, boron, right? Configuration is 1s2, 2s2, 2p1. This is the configuration of boron in ground state. This is the configuration of boron in ground state. And what about the outermost configuration? I'm only going to mention the outermost configuration. This is the outermost configuration of boron in ground state, right? So let's have a look. 2s containing 2 electrons, 2p containing 1 electron, right? Which kind of hybridization is involved? sp2 hybridization. First of all, how many bonds are being formed? There are 3 bonds being formed. If 3 bonds are being formed, so how many unpaired atomic orbitals should be here? There should be 3 unpaired atomic orbitals. So in order to get the 3 unpaired atomic orbitals, what should happen? Excitation should happen. One of the electron from here will enter here, right? So after the excitation, the excited state configuration is going to be like this. 1 electron here, 1 electron here. This is the excited state electronic configuration of boron, right? Yes. When the boron is in excited state, this is its electronic configuration. Now which hybridization is involved? sp2. So this s orbital, this p orbital and this p orbital, they are going to intermix. They are going to intermix, right? So one of the s orbital and 2 of the p orbitals are going to intermix, right? So how many atomic orbitals are basically intermixing? These 3 atomic orbitals are basically intermixing, right? And the number of atomic orbitals intermixed is always equal to the number of hybrid orbitals formed. So if 3 atomic orbitals are intermixing, I'll say 3 hybrid orbitals will be getting formed. I'll say 3 hybrid orbitals will be getting formed. 1 hybrid orbital, 2nd hybrid orbital, 3rd hybrid orbital. And I'll be calling all these hybrid orbitals as sp2 hybrid orbitals. This is sp2, this is sp2, even this is sp2 hybrid orbitals, right? Now there are 3 unpaired electrons. Basically, this will contain 1 unpaired electron, this will contain 1, this will contain 1 hybrid orbital. Unpaired electron, right? Now these hybrid orbitals containing unpaired electrons, they are going to arrange themselves in such a way that there should be minimum repulsions between these hybrid orbitals. And how these are going to arrange themselves, have a look exactly how they are going to arrange. See guys, this is how they are going to arrange themselves such that there will be minimum repulsions between them. This is one of the hybrid orbital. This is one more hybrid orbital. This is one more hybrid orbital. And every hybrid orbital contains 1 electron, right? This is the scenario when the hybrid orbitals are at maximum distance and repulsions between them will be minimum, right? Now once these hybrid orbitals, they have arranged themselves in such a way that there are minimum repulsions between them. Now what is going to happen? These hybrid orbitals are going to show the overlapping, right? Okay, how they are going to show the overlapping? See, Boron is forming 3 bonds. This is boron right now, correct? One of the fluorine will come from this side, one fluorine will come from this side, and one fluorine will come from this side, correct? So if I ask you, what is the configuration of fluorine, outermost configuration? It's 2p5 configuration. Fluorine, 2p5 configuration. 2p containing some 5 electrons. 1, 2, 3, 4, 5, right? Let's call this as px, let's call this as py, let's call this as pz. Okay, so there is one atomic orbital in fluorine which is unpaired, and that atomic orbital of fluorine which is unpaired is going to overlap with these hybrid orbitals, right? Yes, so I'll say px atomic orbital of one fluorine has come from this side and has done the overlapping. So which kind of overlapping this is? This is actual overlapping, leads to the formation of sigma bond, right? Now one more p orbital of one more fluorine atom will come from this side and will do the overlapping, right? Sigma bond. One more p orbital of one more fluorine atom will come from this side and will do the overlapping like this. Yes, so again sigma bond. So how many sigma bonds got formed? See, this is boron, this is sigma bond, this is fluorine, boron, sigma bond, fluorine, boron, sigma bond, fluorine. So this is how your BF3 actually looks like. Yes. Now guys, have a look. This bond, this overlapping is between sp2 hybrid orbital of boron with the pure p orbital of what? With the pure p orbital of fluorine, right? Even this overlap, it is between sp2 hybrid orbital of boron and pure p orbital of what? Pure p orbital of fluorine. Similarly, this overlapping, it is basically sp2 hybrid orbital of boron and pure p orbital of one more fluorine, right? Is the overlapping everywhere same? Overlapping everywhere is same, right? So I'll say extent of overlapping is same everywhere, right? Extent of overlapping is same everywhere. If extent of overlapping is same everywhere, what is going to happen? What is going to happen? If extent of overlapping is same everywhere, I'll say strength of all the 3 bonds is going to be same. And how do I represent it finally? This is boron at the center. This is one fluorine over here making a sigma bond with boron, one more fluorine over here and one more fluorine over here. And this kind of a structure is what we call as trigonal planar structure. We call this as trigonal planar structure. Yes. And this trigonal planar structure, this is the trigonal planar structure. What is the bond angle between these 2 bonds? What is the angle between these 2 bonds? It's 120 degree, as I've told you already, right? This is how your BF3 exactly exists, right? You can let me know in the chats if it is clear so that I can give you a few more examples and every single thing gets clear with that. Let me know in the chats first of all. And the ones who have not liked the video yet, please do like the video, share the video with friends, and do not forget to subscribe to the channel as well, yeah? Right? Perfecto. Let me take one more example so that it gets properly clear, right? See guys, for example, I'm taking the molecule as CH4. I'm taking the molecule as CH4, correct? Let me first of all show you मनफूल दयाल SF4 का बता दो सर यार SF4 का भी बता दूंगा उसकी शेप होती है seesaw shape 4 sigma bonds 1 lone pair right just wait for it let me finish first things right SF4 भी बता दूंगा seesaw shape 4 bond pairs 1 lone pair okay चलिए let's talk about CH4 first of all let me show you how to calculate hybridization in case of this CH4 right this carbon is the central atom right if this carbon is the central atom, how many valence electrons are there with this central atom? 4 valence electrons. Yes. How many terminal atoms do we have? We have 4 terminal atoms. That means there are 4 sigma bonds. See, carbon, its structure is somewhat like this, as you all must be knowing. Carbon had some 4 valence electrons. Out of 4, it is using 1, 2, 3, 4. Out of 4, it has used all the 4 valence electrons for the sigma bonds. So, is there any electron left with the carbon in the valence shell which has not participated in the bonding, right? There is no electron left as such, okay? So how many lone pairs are there with carbon? 0. Carbon had 4 valence electrons and out of 4, it is using all the 4 electrons for the 4 sigma bonds, right? Now, you got to know the sigma bonds, you got to know the lone pairs. Let me calculate the steric number. Steric number is going to be 4 plus 0, that is 4. If the steric number is 4, the hybridization involved is going to be sp3. If hybridization is sp3, the geometry of the molecule is going to be tetrahedral, and if it is tetrahedral, do remember the bond angle in case of tetrahedral structure is 109 degree 28 minutes, right? Okay, this is all about CH4. Yes? right? Now, let me exactly show you how the CH4 actually gets formed, right? Let's exactly see it now, okay? If I talk about carbon, the outermost configuration of carbon in ground state is 2s2, 2p2. This is the outermost electronic configuration of carbon in ground state. 2s containing 2 electrons, 2p containing 2 electrons, right? 2p containing 2 electrons. This is the ground state electronic configuration of carbon. See, over here in this carbon, in the ground state electronic configuration of carbon, there are only 2 orbitals having unpaired electrons, right? But how many bonds this carbon is forming? Carbon is forming 4 bonds. So this carbon should have 4 unpaired orbitals, 4 unpaired orbitals. So for that, in order to get the 4 unpaired orbitals, what is going to happen? One of the electron will go to this one. One of the electron will go to, this p orbital, right? So what is going to be the excited state configuration of this carbon? Excited state configuration of this carbon is going to be like this. 1 electron here and 3 electrons here. What kind of hybridization is involved in case of CH4? sp3 hybridization, right? sp3 hybridization. This is s orbital containing 1 electron. This is one of the p orbital containing 1 electron, one more p orbital containing 1 electron, one more p orbital containing 1 electron. Which kind of hybridization is involved? sp3. So all these 4 atomic orbitals, they are going to intermix. So they are going to intermix. And when they intermix, they will lead to the formation of hybrid orbitals. Since 4 atomic orbitals are intermixing, so 4 hybrid orbitals will be getting formed. 4 hybrid orbitals will be getting formed, right? And these hybrid orbitals are going to be like this. So since 4 atomic orbitals intermixed, so 4 hybrid orbitals got formed, right? And every hybrid orbital is going to contain 1 electron. Yes. Now these hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions between them. That is only possible when these hybrid orbitals are at angle of 109 degree 28 minutes, right? Okay, so let me arrange them. I have to arrange these hybrid orbitals in such a way that there should be minimum repulsions between them. This is one hybrid orbital. This is one more hybrid orbital. This is one more hybrid orbital. And this is one more hybrid orbital, right? Yes, every hybrid orbital contains 1 electron. Okay? Right? Now people, what is going to happen? See, this is carbon basically. Now there are 4 hydrogens, right, which are going to come. What is the configuration of hydrogen? It is 1s1. It is 1s1 configuration, like this. It is 1s1 configuration. So I'll say one of the hydrogen will come from this side, one from this side, one from this side, and one from this side, right? So it is basically the s orbital of hydrogen which is coming for overlapping. Let's assume this is the s orbital of hydrogen which has done the overlapping with this one, right? One s orbital of another hydrogen has come for the overlapping, right? One more 1s orbital of hydrogen has come for the overlapping. One more 1s orbital of hydrogen has come for the overlapping, right? So what kind of overlapping this is? See, first of all, is it the head-on overlapping? Absolutely, it's the head-on overlapping. It's the axial overlapping. Axial overlapping always leads to the formation of sigma bond, right? So this is basically a sigma bond which got formed. This is sigma bond, this is sigma bond, this is sigma bond, right? Now people have a look. What kind of overlapping is here? It is basically the overlapping between sp3 hybrid orbital with s orbital of hydrogen. This one is again sp3 hybrid orbital of carbon and s orbital of hydrogen. Again, sp3 hybrid orbital of carbon, s orbital of hydrogen. sp3 hybrid orbital of carbon and s orbital of hydrogen. Is the type of overlapping same everywhere? Absolutely. Everywhere we have got same type of overlapping, right? If everywhere we have got same type of overlapping, so the strength of bond, so I'll say extent of overlapping everywhere is going to be same. And if extent of overlapping is same, strength of bond is going to be same everywhere. So all the 4 bonds which got formed in this case, they are going to have the same strength, right? They're going to have the same strength. Yeah. So how do I represent it finally? This is carbon which I'm showing over here, this carbon. There is 1 hydrogen over here, 1 more hydrogen over here, 1 more hydrogen behind this carbon, and 1 more hydrogen over here. And we call this shape over here as tetrahedral shape. We call this geometry as tetrahedral geometry. We call this geometry as the tetrahedral geometry. Yes. And in case of tetrahedral geometry, if I ask you what is the bond angle, you should say 109 degree 28 minutes. I'm sure it's clear to everyone. You can let me know in the charts if every single thing is clear so that I can move on to the next one, right? Let me know fast, people, if every single thing is clear till here. This is how your CH4 is actually formed, yeah? Perfect, guys. So let's move on. Let's take few more examples, right? Let's take few more examples. For example, I'm taking the case of PCl5, right? I'm going to take the case of PCl5, correct? First of all, in PCl5, this phosphorus is the central atom. Phosphorus belongs to group 15 elements. If phosphorus is a group 15 element, how many valence electrons it will be having? It will be having 5 valence electrons. How many terminal atoms do we have? We have got 5 terminal atoms, 5 chlorine atoms, 5 terminal atoms. The number of terminal atoms is always equal to the number of sigma bonds. So 5 sigma bonds basically, right? Phosphorus is basically making how many bonds? 1, 2, 3, 4, 5, for example, right? This phosphorus, it had some 5 valence electrons, and out of 5 valence electrons, it's using all the 5 valence electrons. Phosphorus is using all its 5 valence electrons to form 5 sigma bonds, right? So will there be any electron left as such on phosphorus from its valence shell which has not participated in the bonding? No. So I'll say there is no lone pair on phosphorus. Lone pair is 0. So if you got the number of sigma bonds, you got the number of lone pairs. If I ask you what about the steric number, you will say sigma plus lone pair, 5. If the steric number is 5, you will say the hybridization is going to be sp3d. This is the hybridization, right? In case of sp3d hybridization, it is always the dz square atomic orbital which is involved in the intermixing. It is always the dz square atomic orbital which is involved in the intermixing in case of sp3d hybridization. And remember, in case of sp3d hybridization, the geometry is going to be trigonal bipyramidal. Trigonal bipyramidal, correct? Now see exactly how this PCl5 gets formed. This was the data about PCl5. Now let's have a look of how this PCl5 is actually formed. Have a look, guys. See. First of all, what do I need to do? See. Let me take phosphorus in its ground state. What is the configuration? Right? See, phosphorus, it comes under the nitrogen family. In case of nitrogen, what is the outermost configuration? 2s2, 2p3. So its outermost configuration is going to be 3s2, 3p3. There will be 3d also, but containing 0 electrons. This is the ground state electronic configuration of phosphorus, right? 2 electrons over here in 3s, 3 electrons over here in p, and no electron over here in d. Right? No electron over here in d. This is the ground state electronic configuration of phosphorus, correct? Now we will have a look. How many unpaired orbitals do we have right here? We have got 3 unpaired orbitals, right? So if it has 3 unpaired orbitals, how many sigma bonds it should form? How many bonds it should form? It should form 3 bonds. But over here it's forming 5 bonds. So what should happen? Excitation should happen, right? So this phosphorus, one of the electron from 3s will enter into 3d. So its excited state configuration is going to be like this. This is the excited state configuration of phosphorus, right? Now, how many unpaired orbitals do we have? Now we have 5 unpaired orbitals, right? Yes? Now we have got some 5 unpaired orbitals, right, people? So how many bonds it's going to form now? 5, yeah? Now, what kind of hybridization is involved? It is sp3d hybridization. So see, this is s orbital basically, this is p orbital, this is p orbital, this is p orbital, and this is dz square orbital, right? These orbitals are going to intermix and they will lead to the formation of what? They will lead to the formation of hybrid orbitals, right? So how many atomic orbitals are intermixing? 1, 2, 3, 4, 5. 5 atomic orbitals are intermixing. If 5 atomic orbitals are intermixing, it will lead to the formation of 5 hybrid orbitals like this. It will lead to the formation of 5 hybrid orbitals like this. Right? So every orbital will contain one electron. Yes. And at the same time, I'm calling every hybrid orbital over here as sp3d hybrid orbital, right? This is sp3d hybrid orbital. This is again sp3d hybrid orbital. Again sp3d hybrid orbital, right? Now, people, the point is, we need to arrange these hybrid orbitals in such a way that the repulsions between them should be minimum, stability should be maximum, right? Now, how do we arrange them? How do we arrange them? Have a look, how do we arrange them? See, guys. This, for example, one of the hybrid orbitals. Right? This is one more hybrid orbitals. So this is hybrid orbital containing 1 electron, hybrid orbital containing 1, hybrid orbital containing 1 electron. So total I have 5 hybrid orbitals, right? Out of 5, these 3 hybrid orbitals will be present in the same plane. These three hybrid orbitals, they'll be present in the same plane. Now, how many hybrid orbitals do we have left? We have two hybrid orbitals left, right? So, this is, for example, one more hybrid orbital which is present perpendicular to the plane, right? Upwards. And there'll be one more hybrid orbital which is present perpendicular to the plane but downwards, right? Even this contains one electron, this contains one electron, right? Three hybrid orbitals are present on the plane. One will be above the plane, one will be below the plane, right? Yes. Now after this. Now 5 chlorine atoms are going to come and will start doing overlapping with these 5 hybrid orbitals, right? So if you talk about the electronic configuration of chlorine, outermost configuration is 3p5, right? 3p5. If it has got outermost 3p5 configuration, 1, 2, 3, 4, 5. Let's assume this is px, this is py, this is pz of chlorine, right? I'll say one of the px atomic orbital of chlorine will come from this side and will do the overlapping, leads to the formation of sigma bond. One more p orbital of one more chlorine will come from this side and will do the overlapping, right? One more p orbital of one more chlorine will come from this side, will do the overlapping, right? One more p orbital of one more chlorine will come from this side and will do the overlapping. Yes. And one more p orbital of one more chlorine will come from this side and will do the overlapping, right? So everywhere you can see it is the axial overlap, head-on overlap. Head-on overlap always leads to the formation of sigma bonds. So how many sigma bonds got formed? 5 sigma bonds got formed, right? 5 sigma bonds got formed, correct? So how do I represent it finally? This is phosphorus present at the center. There'll be 3 chlorine atoms with the phosphorus which are present on the same plane. This is the plane containing phosphorus and 3 chlorine atoms. There'll be 1 chlorine perpendicular to the plane like this. There'll be 1 more chlorine perpendicular to the plane like this, right? And if you look at this structure exactly, right? If you look at this structure exactly, just a second guys. Did I miss some? Yes, I missed this one. Okay, if you look at this structure exactly, it is something which we call as trigonal bipyramidal structure. This is your trigonal bipyramidal structure. Yes, these bonds which are present on the same plane, these are what I call as equatorial bonds, right? Equatorial bonds. And these bonds which are present above and below the plane, right? These are what I call as axial bonds. Remember, the axial bond length in case of trigonal bipyramidal geometry is greater than, the axial bond length is going to be greater than that of equatorial bond length, right? Do remember this as well, right? Since this is the chlorine present at the axial position, this chlorine is going to experience repulsions from these equatorial chlorines, due to which this chlorine will go a little far, due to which this bond length increases, right? As simple as that. Axial bond length is going to be greater than that of equatorial bond length. Do remember this thing as well, right? So this was all about what? This was all about your PCl5. One thing I forgot, this angle is going to be 120 degree, right? This angle between these two is going to be 90. Even this and this 90. Even this and this is going to be 90, right? These are 3 bonds present on the same plane, one perpendicular plane, one below the plane, right? Perpendicular, right? So how many 120 degree angles we have? We have got 1, 2 and 3. We have got 3 120 degree angles, right? Yes. We have got 3 120 degree angles. And if I ask you how many 90 degree angles we have, see this bond is making 90 with this one, even this bond is making 90 with this one, this bond is making 90 with this one. So 3 above the plane and similarly 3 below the planes. So there'll be 6 90 degrees over here in case of this trigonal bipyramidal geometry, right? I'm sure it is clear to everyone. Right, people? Should I move on? Aman, you can drag the video a little back. It'll be a replay for you, right? Perfect. Let me take one more example. That is, for example, SF6, correct? SF6 I'm taking. Sulfur, it has got some 6 valence electrons. How many sigma bonds do we have in this case? 6 sigma bonds, right? How many lone pairs are there with sulfur? Since sulfur has some 6 valence electrons and it is using all its valence electrons to form 6 sigma bonds, so there will be no lone pair on sulfur. So if I ask you about the steric number, it's sigma plus lone pair, 6 plus 0 comes out to be 6, right? What about the hybridization? It's going to be sp3d2. This is the hybridization. And in case of sp3d2 hybridization, remember, it's going to be dz square and dx square minus y square, which participates in the intermixing, which participates in the hybridization. The geometry over here in case of sp3d2 is going to be octahedral. It's going to be octahedral, right? Yes. Now have a look exactly how it's going to get formed, right? And this is the last example which I'll be taking in the night session. Rest we'll be discussing in the next session, right? I'm going to continue the hybridization in the next session as well, right? I did not finish the hybridization yet, okay? This concept, this topic of hybridization will be done, will be continued in the next session as well, yeah? Have a look, guys. If you talk about sulfur, sulfur belongs to oxygen family. The outermost configuration of sulfur is 3s2, 3p4. And there is 3d as well, which contains 0 electrons, right? This is the ground state electronic configuration of sulfur. Right? This is the ground state electronic configuration of sulfur, right? Now we will have a look. How many unpaired electrons do we have in this case? 2 unpaired electrons. How many bonds it's forming? 6. So we should have 6 unpaired orbitals over here. In order to form the 6 bonds, yes? Yes, Faisal. In order to make 6 bonds, we should have 6 unpaired orbitals over here. So what should happen? Excitation should happen. One of the electron from here to here, right? One of the electron from here to here, right? Excitation. So what is going to be the excited electronic configuration? 1 over here, 1 over here, 1 over here, right? And these are 2 over here, correct? Since the hybridization involved is sp3d2, hybridization involved is sp3d2, right? This is S, this is P, this is P, this is P, this is D, this is D, right? So these orbitals are going to be, these atomic orbitals, they are going to be intermixing, right? They'll intermix. They will intermix and they will lead to the formation of what? They will lead to the formation of hybrid orbitals, right? So how many atomic orbitals are mixing? 6 atomic orbitals are mixing. If 6 atomic orbitals are mixing, how many hybrid orbitals will be getting formed? 6 hybrid orbitals will be getting formed. Now we have to arrange those 6 hybrid orbitals containing electrons in such a way that there should be minimum repulsions between them. I'm directly making that shape, right? I'm directly making that geometry. This is one hybrid orbital containing 1 electron. One more hybrid orbital containing 1 more electron. One more hybrid orbital containing 1 more electron. One more hybrid orbital containing 1 electron, right? These 4 hybrid orbitals, they are present in the same plane. These 4 hybrid orbitals, they are present in the same plane. There will be one hybrid orbital which is going to be perpendicular to the plane like this upwards, and one more hybrid orbital perpendicular to the plane but downwards like this. Even this carries 1 electron, this carries 1 electron, right? Now, sulfur is forming bonds with fluorine, right? What about the outermost configuration of fluorine? It is 2p5. It is 2p5, right? It is 2p5. 1, 2, 3, 4, 5, right? This is px, for example. Now, one of the px of one fluorine will come from this side and will do the overlapping, right? It's a sigma bond. One more, I'm not showing in this way. Now, let's say this fluorine atom coming here, doing the overlapping. One fluorine atom, one more fluorine, one more fluorine, one more fluorine, one more fluorine. But you should understand, it is basically the p orbital of every fluorine atom which is going to come and do the overlapping, right? So how many sigma bonds got formed? I'll say 6 sigma bonds got formed. 6 sigma bonds got formed. Every overlapping is between sp3d2 hybrid orbital of sulfur and p orbital of fluorine. This is the type of overlapping in every sigma bond over here. Yes? Right? We call this geometry as the octahedral geometry, and let me show you how it exactly looks like. This is sulfur, this is fluorine, one more fluorine, right? One more fluorine, correct? So these are basically 4 fluorine atoms on the same plane. There will be one fluorine atom perpendicular to the plane like this, one more fluorine atom perpendicular downwards, right? As you saw exactly in this one. If you join these, if you join it like this, the structure, the shape is going to be like an octahedron. The shape is going to be like the octahedron. So this shape is what I call as octahedral shape, right? So if I ask you, how many 90 degrees do we have in this case? See guys, this bond is making 90 degree with this one, with this one, with this one and this one. So 490 degrees from the top. Similarly, 490 degrees from the bottom. Even this will be 90, this will be 90, this will be 90, this will be 90, because there's a square and diagonals of the square cut at 90 degree, right? Okay, so how many 90 degrees are there in total? There are total 12 90 degrees in case of what? 12 90 degrees in case of your octahedral geometry. I'm sure it's clear to everyone. Yeah. Let me give you one homework. You guys are going to let me know its answer in the chats, right? I'm going to give you the molecule, for example, SF4. Do let me know its hybridization. Do let me know its hybridization. I'm taking the molecule as PCl3. Do let me know its hybridization in the chats. I mean, in the comment section afterwards, right? Then I'm giving you one more molecule as simple molecule I'm giving you. Let's say BCl3. Do let me know its hybridization, right? I'm giving you H3O positive as well. Do let me know its hybridization as well. Do let me know the hybridization of all these species, right? I did not end the hybridization topic yet, right? I did not end it. I'm going to continue this hybridization topic in the upcoming session, right? So with this, I'm going to take a leave. And if you're not liked the video yet, please do like the video, share the video with friends, do subscribe to the channel, do not forget to hit the bell icon so that you get the notification of every single session which we take live on this channel, right? And if you're not enrolled into the actual Vedantu platform, right? If you're preparing for NEET 2023, right? Let me tell you, we have got the actual batches going on the actual Vedantu platform, right? In order to be part of those batches, you need to take any of these pro subscriptions, right? All these pro subscriptions are basically valid for 2 years, right? All these pro subscriptions are basically valid for 2 years. You can have a look exactly. For example, if I talk about the light subscription, yes, it's valid for, it's a 2-year classroom program, and this much is the course fee. No need to pay this much of amount in one go. You can pay this much of amount in installments as well, right? Similarly, this is one more program, this one more program. You can take any of these programs if you want to be with us for 2 years on the actual Vedantu platform and get trained by the teachers of your choice in every subject, physics, chemistry, as well as biology, right? Well, if you have no idea how the actual Vedantu platform looks like, if you want to see it, if you want to have a demo session, for example, right? You can take this subscription for a month. For a month, you can join the batch, the actual batch, which is on the actual Vedantu platform, right? And for that, you have to pay this much of amount. And after a month, if you think you are getting benefited, then you can continue with this pro subscription. Then you can continue in the same batch, right? But you have to enroll at that time into this pro subscription through 2-year classroom program, right? Similarly, one more, everywhere you can give it a try for a month, right? Everywhere you can give it a try for a month. See if it is working for you, and definitely you're going to love it. Trust me on that. Okay? And let me show you exactly how to get enrolled into the long-term batch, into the batch which is there on the actual Vedantu platform. This is the video which you guys are currently watching, right? You need to drag this video a little down. After dragging this video a little down, click on this show more. After clicking on this show more, guys, you have got a lot of links for you. See exactly. Majority of the students currently are looking for CBSE Term 1 crash course. If you want to go for the CBSE Term 1 crash course, you need to click on this CBSE Science Term 1 crash course. Click on this link. After clicking on this link, you can choose your plan, light plan or classic. This one is for 27, this one is for 3K. You can click on this buy complete course, and do not forget to use the coupon code WSPR, right? Buy complete course, give your number, give your email ID on which you get the OTP, right? This was for the ones who are looking for the CBSE Term 1 crash course, right? If you want to be with us for the 2 years, if you want to take the subscription for a month, right? For the 2-year batch, for the NEET 2023 batch, right? Okay, you need to click on this link, NEET 2 years. Click on this link, and after clicking the link, you can choose your plan, either light or classic or plus, right? For example, I'm going for light plan, okay? And I'm going to give it a try for a month. I need to click on this. After clicking on this, I'll be giving my number, my ID, on which I'll be getting the OTP and everything, right? Yes? Yes. It is not necessary to pay the entire fees in one go. You can pay it in installments as well. Vedantu has kept an option for that as well, right? So do get enrolled, guys. It's going to be, trust me, highly beneficial for you, yeah? So with this, I'm going to take a leave. It was nice meeting you in the tonight's session. I'll see you guys in the next session, in which we'll be continuing with the hybridization part 2, yeah? So with this, I'll take leave. Do let me know the answers of the homework questions in the comment section afterwards, right? So take care, bye-bye, God bless you all, and love you all. Take care, guys, bye.